the database updated but the message broker failed, your system state is now corrupt because the order exists in the table but never reached the shipping service. Writing to two separate resources lacks a shared global lock. If the application crashes between the database commit and the producer send, the data is lost forever. Solve this by using the Transactional Outbox pattern. You write the business data and the message to the same database using a single local transaction. Create an outbox table with columns for message identifier, payload as JSON, destination topic, and a status flag. This table acts as your temporary message buffer. The application issues two insert statements within a single begin and commit block. The database ensures that either both records are stored or none are. A separate process, the relay, reads new entries from the outbox table and publishes them to Kafka. This decouples the business logic from message broker availability. One way to implement the relay is a polling publisher. It periodically queries the database for rows where the status is set to pending. Polling creates database overhead and increases latency. Short intervals consume CPU cycles even when no data is present, while long intervals delay message delivery. A better approach is change data capture. It tails the database transaction log, capturing inserts into the outbox table with zero impact on application performance. Debezium is a popular open-source tool for this. It monitors the database logs and automatically streams every change event into a Kafka top. For systems requiring exactly one semantics, Kafka provides a transactional API. It allows you to send messages across multiple topics as a single atomic unit.
To enable transactions, set the transactional ID property in your producer config. This unique ID identifies the producer instance across restarts to prevent zombies. Call the init transactions method before sending any data. This registers the producer with the broker and closes any lingering transactions from previous runs. Kafka uses a transaction coordinator to track the state of ongoing transactions. It maintains a transaction log to ensure progress can be recovered after failure. Wrap your producer send calls in a begin transaction and commit transaction block. Messages remain in Kafka but are invisible to consumers until committed. Consumers must be configured with the isolation level set to read committed. This prevents them from seeing messages belonging to aborted or ongoing transactions. If the database insert fails, call the abort transaction method on the Kafka producer. This ensures that no orphan messages are left in the stream. Do not attempt a standard two-phase commit between a database and Kafka. It is complex to implement and significantly reduces the availability of your system. The combination of the Transactional Outbox and Kafka transactions provides exactly one semantics. This means effects are reflected in the system precisely one time. Kafka fences out old producers using an epoch number. If a new instance starts with the same transactional ID, the older instance is immediately blocked. Even with transactional producers, consumers must be idempotent. They should check if a message identifier was already processed before applying business logic changes. Use a unique business key, like an order ID, to enforce idempotency in the destination database. An upsert operation ensures you do not create duplicates. Index the outbox table on the status and creation time columns. This allows the relay to quickly identify and process pending messages without full table scans.
Read rows from the outbox in batches. Processing 100 rows in a single database round trip is much faster than 100 individual queries. The outbox cable will grow indefinitely if not managed. Implement a background task to delete or archive rows that have been successfully published to Kafka. If the relay fails to send a message, it must retry. The outbox status should only be updated to completed after Kafka acknowledges receipt of the record. Store the message payload in a format that supports schema evolution, like Avro or Protobuf. This ensures the relay can handle changes in data structure. Integrate the relay with a schema registry. This validates that every message written to the outbox matches the contract expected by downstream consumers. Monitor the number of pending rows in the outbox table. High lag indicates the relay is falling behind, which increases the latency of your entire system. To scale the relay, use multiple instances, but ensure only one processes a specific partition. Use database locks or a coordinator to avoid duplicate processing. If a specific outbox entry consistently fails to publish, move it to a dead letter table. This prevents a single corrupt record from blocking the entire relay. This pattern prioritizes consistency. While it adds a small amount of latency, it guarantees that the external world eventually sees the exact state of your database. In Spring Boot, use the transactional annotation on your service method. Inject a repository to save both your entity and an outbox event in one call. The outbox event should include a trace identifier. This allows you to track a request from the initial database insert all the way through the Kafka pipeline.
Log tailing is invisible to the application.
It captures deletes and updates too, which is harder to do with a simple polling outbox table approach. PostgreSQL offers a listen and notify feature. You can trigger a notification upon outbox insertion, allowing the relay to wake up instantly without aggressive polling. Store metadata like event type and source system in Kafka headers. This allows consumers to route and filter messages efficiently without parsing the entire payload. Maintain order by using the same partition key for related events. The relay must preserve the database insertion order when publishing to the Kafka topic. In multi-region setups, ensure the outbox relay publishes to a local Kafka cluster. Use cross-cluster replication for global data distribution to minimize latency. Verify atomicity by simulating a crash right after the database save. Check that the message appears in the outbox, but is only relayed once the system restarts. The idempotent producer uses sequence numbers for every batch. If a broker receives a duplicate sequence number, it discards the batch, but returns a successful acknowledgement. Running the cleanup job during off-peak hours reduces contention. Use a timestamped-based delete query to remove rows that are older than 24 hours. Transaction lag is the time difference between database commit and Kafka availability. High lag breaks real-time expectations and should trigger engineering alerts. Choose the outbox pattern when the database is your primary source of truth. Use direct Kafka transactions for stream processing tasks within the Kafka ecosystem. Wrapping saves in a single transaction ensures that every event represents a committed change. This is the foundation of reliable, professional distributed systems.